Which problems might you encounter when you do regression analysis? There are actually three quite common problems that you might encounter. One is changing a variation in the data. And if you have x here and y here, and you have this regression line, and you think that, well, this regression line fits my data, but your data is actually something like this. Okay, so it's the variation in the data increases with increasing x. Okay, then that might be a problem, and you might have some outliers. And maybe you have some data here, but over here is 1 point. So what's the effect on that point on your regression line? And you might have dependence among observations. This is often observed in time series data. And then you have the y, that's y and x, but on the x-axis often you have time. Okay, and maybe you fit a regression line, but the residuals are not independent. Sometimes they are above the line and sometimes they are below the line, and there is like a persistent pattern or seasonality to it. So we're going to see the consequences of these problems, how to detect these problems, and how to solve these problems. So, for example, changing a variation and how to detect changing variation. Well, the most easy way to detect this changing variation is to plot your data. Okay, plot your data, and here you have the residuals versus the x. Okay, because then you have removed the effect which has already been explained by x, and then you see whether or not there is something else going on, which is not which is not explained by your regression line. So for example, here you have some low variation, whereas here you have some high variation. Okay, and if these residuals have a different variance, then they are heteroscedastic. Okay, whereas if they have the same variance, they are so-called homoscedastic, and that would be if the residuals, the errors, were kind of equally scattered around the zero line. Okay, even depending on x. And the simple regression model assumes homoscedasticity. Okay, and that's because the consequence of heteroscedasticity is that the prediction intervals are too wide or too narrow. Okay, so you can see that if you have sorry, if you have x here and y here, and you have like a regression line or y hat, and you kind of have these prediction intervals. Okay, then these prediction intervals, they are made based on one standard deviation of the residuals, right? And you use that standard deviation of the residuals, or root MSE, to create the upper bound and the lower bound for any prediction from this regression line. Sorry. And if the data are not very scattered down here, but they are very scattered for large X, then you see that the prediction interval for low X for Y given low X is too wide, and the prediction interval for an X nu which is high, or the prediction interval for large X is too small, right? It's too narrow. Okay, and in addition, the confidence intervals, so the prediction intervals, they are these vertical lines, and confidence intervals, they are these horizontal lines, right? And the confidence intervals for the slope and intercept, they are not reliable. And because these are not reliable, then the hypothesis tests regarding the true parameter values are not reliable. Okay, and there are two solutions. Two solutions. I can do like this. Two solutions, and one is to transform your variables. Okay, okay, and that's not often quite easy. Okay, so but the easiest, it's number 2 here. Okay, use standard errors that are robust to heteroscedasticity, and you can automatically get these standard errors which are robust by including this term in your static command. Okay, just type regress x and y on x given robust standard errors, and then you can interpret the t values and the standard errors and the confidence intervals just as if you did not have heteroscedasticity. Okay, and outliers, how to detect them? Well, you of course plot. You plot the y versus the x, and then you can see whether or not there's a group and there's an outlier. And then what you can do is to estimate the regression line without the outlier, and you have the y hat or regression with outlier. Okay, and the reason why you would do this is because you have to look at the consequence of including the outlier and not including the outlier. And then you can use the standard errors obtained excluding the outlier to compare the estimates. Because if these estimates of the intercept and the slope do not differ much, then there is no problem including the outlier. But these differences, they have to be measured with in a certain, what do you say, on a certain scale. And the scale we use is the standard error of the parameter, no, the intercept or the slope. I kind of lost my thought here. I have to regress. Okay. So you just take the estimate of the intercept or the slope, and you look at the difference. For example, here with the difference in the intercept with outlier, it's 5,887, and without outlier, the intercept would be 1,558, and this difference you measure by looking at the standard error of the intercept without the outlier. Okay, so that would be 2,877. So that would be so the difference between these two estimates, they are 1.5 standard errors apart. Okay, they are 1.5 standard errors apart, which is quite a bit. So in Stata, you can combine regress with the if statement to exclude outliers, and you do that by taking regress y on x, and you say if x is not equal to 900, then you get the regression line without outlier. And 900, that's because here we have this x. For x equals 900, we have this outlier. Okay. So then you would get both these regression lines quite easily. Okay. And the key issue here is whether or not to keep the outlier when you do the analysis. And what you can think of is you have to think logically. Okay, if the outlier is a logical value, given that x value, then you should include it. Okay, so if the next time x is around 900, then the y value would be around 28,000 or 29,000. Then you should keep it. Okay. But if the outlier is the result of a mistake of data, it should be excluded. And obvious errors would be like a negative age or negative sales in the data, but often you can't decipher like an error from the rest of the data. So you have to know your data set and where it comes from whenever you do analysis. Okay. So that's actually the first thing you do. You try to know your data and where it came from. So, and if you exclude any data from your analysis, then you have to explain what was deducted from the data and why. Okay, so the last problem is dependent errors. Okay, for example, in time series data, you have these tables with date, and for each date it can be day 1 and day 2 and so on, and these would often be numbers. They could also be years or months or weeks. As long as they are numbers, then you can run a regression on them quite easily, and then you have a y value. Maybe this is sales. Maybe it's sales. So for example, on day 1 you sold goods for 540,000, and on day 2 you sold goods for 625,000, and so on, and then you can kind of run a regression across time, and by doing this you get some residuals, and often you have kind of seasonality in your data. Okay, because if you look at several years of sales, and you have monthly sales of, for example, ice cream, then you would kind of, even though your regression line is linear, you would see this seasonal pattern where you sell more during the summer months and less during the winter months of ice cream. And you can detect this seasonality by plotting residuals versus time. And here you see there's definitely like persistence of these residuals to either be above 0 or below 0, which means that residuals which are negative are often followed by negative residuals, and residuals which are positive are often followed by a positive residual. Whereas on this is then dependence of residuals. And here you kind of have no evidence of dependence. Okay, and here you probably should have time. Maybe it's it's the number of hours or minutes or days or weeks or years, maybe a long time series. Okay, so this is one way of detecting that there might be a problem of dependent residuals, and we can also use like an econometric method. We can use the Durbin-Watson test, and the Durbin-Watson test actually tests whether or not the correlation between errors are equal to 0 or different from 0. So it usually tests the correlation between the residual, the error of time t against the correlation of the error at time t minus 1. For example, if positive residuals are followed by positive residuals, and negative residuals are followed by negative residuals, then you would have a positive correlation, okay? Because then you would have this if this is the errors, and this is time, and you would have like positive residuals following positive residuals and negative residuals following negative residuals, then you would have like a positive correlation, okay? Correlation between the residuals at time t and the residuals at time t minus 1 would be positive, would be greater than 0. Whereas if you have this pattern of errors, that a positive residual is followed by a negative residual, and a negative residual is followed by a positive residual, and so on, then you have like a correlation of these residuals t minus 1 of less than 0, like a negative correlation, okay? And the alternative hypothesis is actually or not equal, so let's see, is actually the correlation between the errors would be different from 0. Okay, so and if you have these correlation structures across time, then you call this autocorrelation. Okay, you say that the residuals or the errors of the regression are autocorrelated, and the Durbin-Watson statistic, it's just calculated as d equals the squared differences, the squared differences of these errors, and you sum them. So this is just the sum of the ET minus ET minus 1, and you square them, divided by the sum of the ET squared. Okay, and this Durbin-Watson statistic, it's also possible to calculate this by just taking 2 minus 2 times the correlation of the errors. Et minus 1. Okay. Which means that you immediately see that the correlation can only be between +1 and -1, and which means that this part here can only be between -2 and 2, which means that the Durbin-Watson statistic can only take numbers from 0 until +4. Okay, and we're going to look at that, because if you take the correlation of the errors, the autocorrelation T minus 1, and you have this, let's see, how can you do this? Oops, that was too much. Taken away, T minus 1, and let's see, we can have this, yeah. Okay, from actually -1 to 1 and 0 here, then if we have this correlation range, then we have the Durbin-Watson range here. Okay, and the reason why I took -1 correlation here was that this implies a Durbin-Watson statistic of 4, and a correlation between these errors, a perfect positive correlation between the errors, corresponds to a Durbin-Watson statistic of 0. So what you can say is that like if the Durbin-Watson statistic is less than this critical value, then you have a correlation of the errors which is positive, and if the Durbin-Watson statistic is greater than this critical value, then you have a correlation of the errors, an autocorrelation, which is negative. And a negative autocorrelation is extremely seldom to see. What you often expect is to see a positive autocorrelation. And if the correlation between the errors are 0, then you would get a Durbin-Watson statistic of 2. So if the Durbin-Watson statistic is vastly different from 2, either on the upside or the downside, then you have autocorrelation. And an interesting point here on the graph is that if you have kind of correlation of negative 0.25 or a correlation of 0.25, then that corresponds to a value of 2.5 for no, sorry, a value of 1.5 for a positive correlation, and a value of 2.5 Durbin-Watson statistic for a a negative correlation, autocorrelation. So and these numbers, they are quite close to these these critical values. So if you don't have this table, but you have the Durbin-Watson statistic, then if you get a value below 1.5, then you should be skeptical. Okay. And we have the consequences of dependent errors, like why is it so negative to get dependent errors or autocorrelated residuals? Because if there is positive or autocorrelation in the errors, the estimated standard errors are too small. And the estimated slope and intercept are less precise than suggested by the output, which means that you get overconfident in your model estimates. Which makes you believe that your model is actually better than it actually is. And the best remedy is actually to include dependence into the regression model. So this actually means that you can include extra x variables. Okay. And if we look at an example, then we have data for 29 years, which means n equals 29. And okay, why does this residual plot indicate dependence? Well, it's really that positive residuals often lead to positive residuals, or positive residuals are followed by positive residuals, and negative residuals are followed by negative residuals. So this clearly does not look random. Okay, so we are given the Durbin-Watson statistic of 0.25, and what does the Durbin-Watson test conclude? And a Durbin-Watson statistic of 0.25 and a number of observations of 29, then we can actually go back to our table and we look here at the n, and we can go down here to find the correct n. We have a number of 29 observations, which means that we would rather err on the downside than the upside, or we would rather have a wider confidence interval than a too narrow one, which means that even though 30 is closer to our number of observations, we are going to use the number 20 here, or the row for 20 observations, because we are erring on the conservative side. So, which means that we are using the critical value of 1.41. Let's see, 1.41, and we compare that 1.41, and we see that our Durbin-Watson statistic is lower than 1.41, which means that we reject H naught of no autocorrelation. Okay, so what we have here is that we have evidence of positive autocorrelation. Okay, so to conclude, we always have to check the conditions for the simple regression model, because if we don't, then we might put more confidence in our estimates than we have reason to. And we have to be aware of potential problems affecting the simple regression model, the three problems that we went through, and what we can do about the problems. And well, you should rely on software to calculate these standard errors, because it's so much simpler, and you have to use the prediction intervals to predict, and you should use the confidence intervals to check if your regression line is different from just using for example, the average value of y to make predictions of y. And of course, this is really important if you have like an outlier, or if you choose to make if you choose to make a prediction for a value of x for which you did not estimate your regression model, then be very careful. Okay, thank you.